Excuse me? That didn't work. Excuse me? I think we're ready to get started here. I am absolutely thrilled to introduce Dr. Larry Hunter this evening. He is professor and director of the Center for Computational Bioscience here in Colorado, among many other illustrious titles. He obtained his bachelor's and PhD from Yale University. Fun facts, in 2003, he was gifted a supercomputer from IBM. The supercomputer had an estimated value of about $1 million. He's done stand-up comedy shows about genetics. I've heard they're so good, no one's been able to replicate it. Okay.
You have a great future.
Thank you.
In medicine.
And lastly, he's been a personal mentor to me on my AI journey with the outstanding Tiffany Callahan. So please put your hands together for Dr. Larry Hunter.
Thank you. That was a very generous introduction. And you should try the stand-up thing. It's fun. I want to try and give you a fairly gentle introduction to AI in medicine, and hope you come away feeling like you understand something like what it's about and why it might matter. One of the reasons it might matter is that graph over there on the right, which is the number of times the words deep learning have appeared in articles in Medline on a log scale. We had one in 1989, and then skip ahead 10 years, and one more. And then there's been this sort of steady growth where there were a dozen, and last year there were almost 10,000. So it's been a huge explosion. I have a bunch of titles on the side. You can kind of get a sense of the many different areas in medicine that have now had publications, at least, around artificial intelligence or deep learning. So it's definitely coming. And so I'd like to give you machine learning in one slide so you understand a little bit about how this works. And artificial intelligence and deep learning and machine learning are largely used interchangeably, but I'm going to try and tease them apart for you a little bit. And I'm going to start with this idea of supervised learning. Supervised learning is a way of training a computer program to be able to do something. And so if you go back in the pre-machine learning era, we had to program a computer to do something. You had to give it explicit instructions about every step. And with the machine learning work, instead of programming, we can demonstrate. We can say, here's a bunch of examples, training text or documents or images, the like. And it helps if you have a large number of these, thousands or millions of them. And what we also need for each one of those training examples, whether they're text or images or inputs of some other variety, is a set of labels that say what kind of thing they are. So I'm going to give you an example a little bit later of looking at retinal fundographs and trying to say retinopathy or no. Okay, and so that's a good example. We have a bunch of training images, and for each one of those images we have a label, yes or no, have the diagnosis or not. We turn those documents or those images into something we call vectors. So we make a fixed length representation of them. And for images, mostly what we do is we take the pixels and we lay them out in a row. So we take a square of 250 pixels or something like that, and lay it out into a 250 times 250 length vector, and that's the feature vector. And we give those vector representations along with the labels, yes or no, for thousands and thousands of examples to one of these algorithms. And there's a whole bunch of different ones. Deep learning is one of them. There's others. And those algorithms come up with some predictive model. And say, okay, I have now digested what the things that have the true diagnosis label versus that don't have the diagnosis label for all of these images, and come up with some model that will allow me to predict which is which. And then I take some new text or new document or a new image, I turn it into that vector of features, and then I run it through the predictive model, and it predicts a label. Okay? And I can do this pretty effectively for a very wide variety of different kinds of tasks, different sort of labelings, and different sorts of inputs. So it's really transformed the way computer vision works. I can, because there's tens of millions of photographs of cats and dogs on the internet, I can really do a good job of training up a system to recognize cats and dogs in photographs. Okay? And that's really a remarkable thing. It was very hard to do that before this learning stuff happened. And there's a bunch of reasons we might care about this. There's a bunch of reasons we could use this. So one thing is these algorithms, once you've trained it up, once you've demonstrated it to be able to, say, pick out images of dogs, then it's very inexpensive. You could run millions of new images through there and classify them as having dogs or not in them, and it costs almost nothing. And it's very fast. We can handle millions and millions of those images, much faster than it would be if we had a room full of 10-year-olds saying, is it a dog or not? Right? So it's inexpensive and scalable and fast. On the other hand, people claim that it's consistent and verifiable. Okay? It really does a good job of saying, yes, this is a dog or not. We can tell whether it's doing a good job. That's a statistical guarantee, and we'll come back to how much you should believe that in a little bit. For some kinds of things, it can be more accurate than human judgment. So these systems can pick up on really subtle cues that are hard to see, but are present there in those images of dogs. And so if the dog is fuzzy and far away, and it's kind of small, and it's got pointy ears, it might still get that right, even though it looks sort of cat-like to me. So it might be more accurate. And one of the goals is that it would be more fair, less subject to social biases. It's an algorithm. It's therefore objective. And so it will pick out dogs or cats, even though, the 10-year-olds that I wanted you to imagine populating the room looking at pictures, they like cats. So they might be less inclined to say dogs sometimes. And so the algorithm would be more fair. So it's possible that we could actually take advantage of these machine learning kinds of tricks and come up with some systems that have real advantages over human beings doing these tasks. And in fact, this has happened to medicine. And I mentioned the retinopathy diagnosis system. And this is one that's particularly interesting. It was just published last fall because it's a prospective, randomized, controlled trial. So it really demonstrated that it's possible for one of these machine learning systems to do a very good job picking out retinopathy from fundographs. And this is a task that ophthalmologists do very reliably. But on the other hand, it takes some training to be able to do it, and ophthalmologists are expensive. So there are 33-ish million diabetics in the United States, almost 500 million of them worldwide. And so if we're going to prevent blindness due to diabetic retinopathy, we need to screen all those folks once a year. And if you took every ophthalmologist in America and had them work 12 hours a day screening diabetics, you wouldn't get to 35 million of them in a year. So the scaling potential here is really impressive. And there's other things that are impressive about this as well. If you think of the global burden, then there's no way we're screening 400 and some odd million people a year. We couldn't pay nearly enough to do it. But if I could train my cell phone to be able to do this, and I could encourage people to actually hold their cell phone up to their eyes really close, then maybe we would be able to do something here using this scale and the inexpensive and the fast nature of this to make a big difference in public health. So there really are a lot of opportunities here for using this machine learning stuff to do some good things. And I'm not the only one who has observed this. There are now a little over a dozen, I think there's 14 on that list, of FDA-approved applications of machine learning across a wide variety of different places in medicine. And they're accelerating. There's a whole lot more. There was 2 in 2017. There were a dozen in 2018 up to when this article was published. There will probably be twice as many this year. It's definitely coming. There are going to be a lot of tools that use these machine learning techniques to provide assistance in one way or another in healthcare. And there are millions and millions of them out there. Okay, these machine learning things are everywhere. Every ad you get served up on the internet, if you have an iPhone 10, that facial recognition thing that says unlocks your phone, all those are machine learning based. But very few of them are FDA approved, which is a much higher bar. And we'll talk about why it's important that it be a higher bar and how we need to be careful about it. But one of the things that's most encouraging about this is these computer programs can sometimes see things that we can't see. And so one of the things that was really surprising about the fundograph work is it turns out, we didn't really know this, but computer programs were really good at picking it out. There's a difference between male and female retinas. And computer programs, these machine learning things, are very good, an area under the curve, roughly a measure of accuracy of 0.97 at picking out gender by retinal photo. Now, I admit there are easier ways to pick out gender when you're confronting a patient, But nevertheless, it's an interesting thing that is in there, and we didn't know that signal was in there. And there have been some other examples where we try to use these kinds of machine learning things to find things that we couldn't necessarily otherwise. And so Apple got a patent for doing a smartwatch ECG and being able to pick out hyperkalemia. Now, if you guys looked at an ECG, you could pick out hyperkalemia, pretty sure. There's pretty clear signals in there. Maybe not you, but your cardiology colleagues. But nevertheless, it's kind of impressive that you can do it from a wristwatch. And furthermore, there might be real assistance, say, in surgery and the like, to pick out during colonoscopy, pick out small polyps. You could really imagine a variety of ways that these tools could make certain tasks easier or more reliable that were important for clinicians to do. Now, machine learning stuff is powerful, and I hope to suggest, and you probably are here because you know it's useful and important, but I want to take a step back and remind you that this is not the AI you see in the movies, okay? This is not something that's going to say, excuse me, doctor, are you sure you know, it's not that. And this is a lovely tweet from the guy who's one of the chief technical people at Microsoft, who points out a difference between machine learning and AI. And machine learning is, if it's written in Python, that's a programming language, then it's probably machine learning. If it's written in PowerPoint, like this presentation here, then it's AI. That's the stuff we can't do yet. And in fact, one of my favorite definitions of AI, because AI has been around for a long time. It was coined in the 1950s, the term artificial intelligence. And in those days, we thought artificial intelligence was going to be playing chess or proving theorems or things like that. And in fact, one of the very first artificial intelligence publications was about a compiler that took code like Fortran and turned it into machine language. In those days, we called it automatic programming and thought it was a kind of artificial intelligence. We no longer think that. It's just a compiler. And so the definition of artificial intelligence is what computers can't do yet is not a bad one. But nevertheless, let's not be too worried about Terminator and you know, you see lots of headlines about how we should stop training radiologists because computer programs are going to replace them completely. All of that is crazy. That's not going to happen. We don't have reliable, you know, self-driving cars yet, let alone reliable automatic physicians. So you guys' jobs are safe. Don't worry. And we do have to worry about the uses that these things are going to put to, by far. So anybody want to guess what's the most profitable application of AI in medicine? Billing. Very good. Billing. Real-world medical AI is all about maximizing reimbursement. There are tons of systems out there that help you coding. Okay, if you type AI medical billing coding, you get 1 million hits. All right, there are thousands of companies that are trying to optimize billing using these machine learning algorithms. All right, and this is, I'm going to editorialize for a second, this is really not a good use of the technology. This is not what we should be doing. And it's really sad because if you look at what we're trying to do with these solutions, and you know, I feel sorry for the OIG. So these are the people who are trying to tell whether or not the bills submitted to Medicare are legitimate or not. This is the Fraud Detection Office for Medicare billing, and you know, I think a conservative estimate is 10% of Medicare is fraudulent. They're using this RStat software package that was created by the Inspector General in the late 1970s. It's the primary tool they're using to detect fraud. Okay, they're up against people who are using very sophisticated techniques to maximize billing, and where the line is between maximizing billing and fraud, I'll let you guys figure out, but this is where AI is being used most. And like the rest of the system, we need to really think about the whole context in which this work is being done and the ways that we can make it better for patients and for society rather than just letting capitalism run amok in all of this and do what it will. So I don't want to be too depressing, okay? Medical insurance companies also buy lots of AI things to try and find this stuff. It's not just the OIG and CMMS. But there are some compelling good applications of this too, and this is one of my favorite ones. So this was really, I think, compelling because of the creativity that the people who did it brought to understanding what the clinical problems are for patients and how to use these technologies to improve patients' lives. And so this is the Mercy Healthcare System and Ayadzi, which is a commercial machine learning AI company. And what they were interested in was, can we reduce the diagnostic odyssey that our patients go through? So when you show up and you have something strange, can we get you to the right clinic the first or second time rather than after 5 different clinics where you didn't get helped? And the answer turned out to be yes. There were tons of data about these odysseys that people went through. So the hospital, basically the billing data was enough. We didn't have to have wildly sophisticated representations of images or the care or the patient even. It was really sort of this financial data, mostly procedure data, using unsupervised learning and some supervised that I told you about. Really made a big difference in directing people to the right clinic the first time. It saved the hospital system a ton of money, it saved the patients a lot of heartache, and presumably it ended up providing better care faster. And so this is the kind of thing we can do if we're creative in thinking about how to apply these technologies. All right? But we have to be really careful when we're doing this. It's really easy to fool yourself in a bunch of ways with this AI technology, and I want to give you a couple of cautions about that. So the first one is to beware of bias in the data. All right, I love this graph. Okay, this is a wonderful BMJ article on biases in electronic health record data. Okay, and what these are is along the x-axis here, we have the time of day that a blood draw was done. Okay, and these are white cell counts. And on the y-axis, we have 3-year survival rate. Okay, and so the blue ones are normal, the red ones are high, and the brown ones are low. Okay, so if you look at sort of 4 a.m. or thereabouts, 4 or 5 a.m., if you have a normal white cell count seen in a blood draw at 4 a.m., your all-cause mortality is much worse than if you have an abnormal white cell count with a draw at 9 a.m. Okay? This has nothing to do with the patient. Okay? This is, if you get a blood draw at 4 in the morning, you're sick. All right? And therefore, you're in trouble. Otherwise, we wouldn't have had that blood draw. So what this is showing us is that if we train on the data that's there in the record, and we just use that without understanding the system that produced that data, we're likely to report on the biases. In this case, this is really just showing something like the clinician's intuition about whether or not there should be a blood draw. Is this urgent or not? That's reflected in the time of day that the blood draw happened. So we have to be really careful about the data we feed into these algorithms because we can go wrong in lots of different ways. The data, particularly health data that shows up in the EMR, is biased in all kinds of interesting ways. It reflects not only the situation, the phenotype of the patient, but also the clinician's understanding. One of the very first, I love this story, I wasn't planning to tell it, but I will. One of the very first machine learning implementations I did. I was hired at the National Library of Medicine, part of NIH, in the early 1990s. And in those days, artificial intelligence was expert systems. People would code up a bunch of rules about how to do something. And my boss had this fairly famous system called AI Room, which made rheumatologic diagnoses based on a bunch of factors. And I trained up a machine learning system. He wanted me to say, okay, you're a machine learning guy. Can you do what my system does? So I took a bunch of his examples and I trained up a system. And it performed about as well as the expert system did, which was okay. And the interesting thing was what variables it used to have this good performance. It looked at what tests were ordered, but not what the results of the tests were. Okay, and it worked great. And in fact, you could flip it on its head and you could make really good rheumatologic diagnoses based on what tests were not ordered for these patients. Okay, because it was really, the tests were there largely to confirm the intuitions of the doc. And so with that particular patient population, I could do a very good job of predicting who had RA versus not by looking at which tests were not ordered. So we have to be careful about what kind of things we use to train these systems. And we also need to recognize that being able to make good predictions doesn't give us a policy. It doesn't say what you should do if you can make that prediction. So for example, using that blood draw example, preventing blood draws at 4 in the morning is not going to save anybody's life. All right, the system says, oh, well, look, if you want to have people have good 3-year all-cause mortality, just don't draw blood in the middle of the night. They'll be fine. No. Okay, prediction is not causal. We need to understand how these predictions can be used to improve outcomes, not just blindly apply this predictive method and say, oh, look, the prediction's good here, prediction's bad there. And so I want to use this as an opportunity to introduce a different kind of machine learning called reinforcement learning. And so reinforcement learning is much less sexy these days than the deep learning, the supervised example, because it's hard to do. But there have been some really impressive achievements in reinforcement learning. And reinforcement learning is pretty straightforward. You have an agent, that's a computer program, and an environment. And the agent observes the environment, makes some decisions, takes some actions. That's a cycle, goes around observing and taking actions. And then every so often, it gets a reward. And the idea is to maximize the amount of reward that you get. Okay, so you can imagine doing this in a variety of medical contexts I'll talk to you about in a second, but this is the basis for AlphaZero. Have you heard about AlphaZero, AlphaGo? So Google trained a computer program that is now the world champion Go player. And that same program is actually one of the best computer chess players, better than any human chess player. And the way that the program learned to play Go and play chess is one of these reinforcement learning algorithms. Okay? And reinforcement learning was just on the outcome. But reinforcement learning is actually really hard compared to that supervised thing I mentioned, and there's several reasons for it. So one is the rewards don't come immediately. When you do something right or do something wrong, the reward may take some time to show up. We call that temporal credit assignment. And so it's really obvious in chess. This is a famous chess game from 8 years ago that I got out in a newspaper. And the red arrows are pointing to errors. Okay, so this is Grandmaster. This was actually the Chinese for the first time beat the Russians in World Chess Championship. And so the Russian guy who was playing white, the numbers to the left, made a mistake at move 26. According to the, I'm not that great a chess player, but according to the analysis that happened after the game. And then black failed to take advantage. At move 28, he could have brought down the gauntlet, but instead let white escape by making the wrong move at move 28. But then white made another error at move 34, and black took advantage and won. So the reinforcement algorithm at the end only gets black won. You have to figure out what of those actions and observations were the important ones. And that's hard to do, although if you play enough games, statistically you can accumulate information about the credit assignment problem. A second problem that shows up is called the exploration-exploitation trade-off. And the issue there is you're trying to get reward, right? So if you know one way to get a little bit of reward, do you just do that over and over and over again and accumulate a little bit of reward? Or do you explore the space and try different things and maybe discover something that'll get you a lot of reward that you can do, or maybe just waste your time exploring parts of the space that aren't going to help you? That's the exploration-exploitation trade-off. And in games and simple things like mazes and chess and Go, it's pretty straightforward what to do, but there are much harder problems we'd like to do. So if you imagine reinforcement learning for clinical decision making, there are a wide variety of different choices, lots of different actions you could take, lots of different observations you could make. So we call it the cursive dimensionality. The task is sort of more difficult because of that. And one of my favorite examples in clinical care is actually a reinforcement learning system that looked at treating sepsis patients in the ICU. And this is worth reading in its entirety if you like this kind of stuff. But basically, there isn't all that much you can do. We do vasopressin, and we do IV fluids, right? And it turned out that the AI policy that it came up with, and there's a complicated simulation system that was based on a bunch of patient data. So the AI system, as it's learning this, didn't get to actually go out and make clinical decisions in the ICU a bunch of times and see which ones worked and all that sort of stuff. It lived in a simulation that was a very accurate simulation, and then came up with this different policy. And it's not that hard to read this, but basically vasopressin earlier and less fluids later turned out to really work. And as a result of the publication of this article, it's gotten a lot of uptake among the clinical population who understand this. It's hard to make these trade-offs, and this is pretty good evidence that they should make the trade-offs somewhat different than they usually have made. And it's a fairly subtle difference. It's not a huge one, but it does make a real difference in patient survival. So there are places we can apply these more complicated techniques if we set the problem up right, get the right data, where we can get outcomes that really matter in difficult clinical problems. So I don't want to be too much of a downer about this stuff. I think it's important and we can have successes. I just don't want you to walk away thinking, oh, this is really easy. All we have to do is, solve this problem with algorithms. You guys have hard problems, so it's not so easy to solve with just algorithms. One thing I want to point out is that the errors that AI systems make are really different than the kinds of errors that human beings make. Okay? And so our intuitions about the system performance, oh, it does a pretty good job. Look, here, this was a hard problem. It got it right. Wow, it must be really good at these things. Just because the AI system gets a bunch of hard problems right doesn't mean, the way if a human being did, it doesn't mean it's not going to get some of the easy ones wrong. Okay? The ability to do some things doesn't accumulate the same way it does in human beings, right? I start you off with easy tasks, make sure you get good at those, then I give you harder ones, and if you can do the hard ones, then I believe you can do the easy ones. For AI systems, we give all the problems all at once, right? Tens of thousands of examples. And just because it's good at the hard ones and it's generally fairly accurate, doesn't mean that the errors it might make aren't going to be really trivial ones. And in fact, if you look, I'll talk a little bit more about Watson as we go along, but if you look at the IBM system that they tried to translate into clinical care and oncology, a lot of the mistakes that Watson made were really dumb. You know, chemotherapy is totally counterindicated in this patient, right? And stuff like that. And it was surprising. The places where it was good, but the places where it made mistakes, they were weird mistakes. They weren't the sort of mistakes a human being who was that good would make. So we have to be careful about that. And there are all kinds of places. So training data biases, the thing I mentioned before, there's lots of training data biases. So there are examples. This is mostly in facial recognition. So there's a woman named Joy Bualimi who tested a bunch of facial recognition software that had been marketed by, I think, Microsoft and Facebook. Both made public face recognition software. And she demonstrated that it works best for white men. It was less accurate at picking out gender in women than it was in men. And it was less accurate at picking out gender in non-white folks than it was in the white folks. So that's not because the algorithm had any built-in bias. It's because the training data was biased. And it's really easy to accumulate biased training data. So when you look at applications in the finance world where we've trained up computer systems to make loan origination decisions, the training data reflects bias in society, so the loan origination machine learning system reflected the same bias that was there in the data. So you have to be really careful about biased data. There are parts of the unexplored parts of the performance space means things that weren't in the training data, right? So if there's, I'm trying to think of some reasonable example. I don't know, take the retinal fundograph example. If there were people with congenital abnormalities weren't in the training set, then trying to diagnose people with congenital abnormalities, probably the system is not going to be very good at. I want to talk more, and I think I have an example, yes, coming up next about adversarial examples. So I'll skip that for a second. And one of the things that's interesting about machine learning systems, particularly the reinforcement learning system, but you can do this with the supervised ones, is one of the advantages is as they get more experience, they can get trained. They can learn more. So you see more things in the implementation phase. They can update themselves and continue to get better. Or maybe not. Maybe they'll drift away from getting better and they'll get worse. Right? So there's no guarantee that as the system changes, it gets better. So continuous learning is not the same thing as improvement. And so we have to worry about that. Do we let these things go? All the FDA-approved systems, by the way, are locked down. They don't change once they're approved. And so maybe we're missing out on an opportunity for the system to get better because there's lots of new examples. But that's currently, the FDA says no. There's even scarier stuff. There's adversarial training. So if I want to fool a machine learning system, I can come up with another computer system that will help fool it. So look at the example at the bottom. So this is a system that labels dogs and cats and pandas and a bunch of other animals and the like. And so this comes up as panda, which is correct on the left. And then I can use a black box attack. If I have my own copy of the algorithm, I can feed it lots of different things and change it a little bit to see if I can get it to change its mind about stuff. And I can guarantee that I can actually find good things. And it doesn't look like much. If I add that little bit of noise, to you, the one on the right looks pretty much the same as the one on the left. To the computer program, it's so different that it calls it a different animal. Okay, and that's called adversarial examples. I can come up with small amounts of noise or change that don't look like any different to the human being, but do look different to the program. And this isn't just with image analysis, by the way. Somebody recently proved this on speech recognition, so that I can have a little in the background that will get your Alexa to order me a bunch of good wine and have it delivered to my house. Okay, it's the same kind of thing. And it's not just the post hoc, I give it a difficult example, but you could imagine inserting bad training data. And so suppose I were a pharmaceutical company and I wanted my treatment to be the one that was recommended by the machine learning system. I might make public a bunch of training data that was sort of subtly biased toward the treatment that I wanted to see happen. Okay, and lots of other independent people could train on that data and it would look like it was doing a good job, but if it got deployed, it would have sort of hidden inside it a bias toward my treatment option. Okay, so we have to be really careful about the way we build, certify, and deploy these things. One thing I want to point out is that patients actually have an opinion about this. AI in medicine is enough of a thing so that a company called Syneos Health did a survey of a bunch of patients of various different kinds and some caregivers, and asked them about what do they think about the role of AI in medicine. And they were mostly okay with it. They didn't have any really bad reactions. One thing that was of great concern for them, that it would make it harder for them to get to a human doctor. So they really didn't want less time with their human clinician. And they were afraid that AI would be used to reduce that. They weren't particularly worried about how it worked or whether it was explainable or who was responsible if it went wrong. Those are things that perhaps more sophisticated viewers of this world care about. And one of the things that was quite interesting was they were more okay with the idea of AI nurses than they were with AI doctors. And the reason for that was they felt like it was difficult to get to nurses, and maybe the AI systems could give them personalized, reliable information sort of the moment they asked. They could just type something into the internet or say something to their phone and get information that they needed in ways that would prevent them from getting access to their docs. And so we need to pay attention to what the patient's perspective are on these technologies as well. All right, I'm going to wind up fairly soon. I want to leave you with the thought that we should not treat AI as all that special. And as you look at all the articles in the popular press and a lot of the internal perceptions in the medical community, we have to be really careful not to allow AI to become snake oil. Okay? There's an awful lot of people touting AI in medicine without careful assessment. I think Watson's probably the worst of this. They put millions of dollars in ads in the Super Bowl and all kinds of stuff, and Watson really did not help. The MD Anderson basically, signed away more than $20 million that they invested in trying to get Watson for oncology without adequate demonstration of any value, let alone worrying about patient safety, and eventually just pulled the chain on it and said, this is of no use to us. And there's a lot of AI outperforms doctor stories that you see both in the popular press and to some degree in the academic press. And we should be very careful about those because they're often extremely narrowly constructed tasks. And yes, it may be the case that some machine learning system outperforms some doc on some very narrow task, maybe even a little bit on that retinopathy task. So it's better than the average ophthalmologist on the retinopathy task, although not quite as good as really expert ophthalmologists. But that doesn't mean that we can immediately get rid of ophthalmologists and substitute a program that can pull out retinopathy from a fundograph, okay? That's just not it. So we need to think about this broader context of the system that it's embedded in. And I've been arguing for some time now that we should use the pharmaceutical industry as a model for how we should think about artificial intelligence in medicine. All right, so we should be very concerned about proof of safety, particularly around that problem of making weird sort of errors. So it's not just the percent correct, it's the kind of errors that the system makes that we need to be paying attention to. We mostly have been focused on efficacy of these things. How accurate is it in making that diagnosis? I think we need to regulate the communications that technology companies use with potential clients when they're trying to sell these kind of systems into the medical system. They should really have a medical affairs equivalent to make sure that they don't exaggerate the performance of these systems. And furthermore, we have to pay attention to whether these systems are still working well. Just because it worked once at the time it was approved doesn't mean that the patient population might drift or other changes might happen that require us to do the equivalent of pharmacovigilance and make sure that things haven't changed out from under us or there isn't some population that's vulnerable to the sorts of errors that these kind of systems might make. So we call that technovigilance in these things. And this is not currently the law. I think it's ethically obvious, but it is not legally the case right now. And so we have to be aware as consumers of this technology about some of the risks that are involved. Make sure we make good decisions about it. And so I will wind up by pointing out that there's all kinds of interesting mistakes that algorithms can make. Statisticians make them too. No AI talk would be complete without an XKCD cartoon. And as you're taking into account the depth of the errors that one could make by using these sort of algorithms, I'd be glad to take any questions that you have.
So I know another area of artificial intelligence is kind of like augmented intelligence, and for lots of folks that we work with, they have cognitive impairments, other things. Can you talk a little bit about kind of where we're at with things that might help augment not so much healthcare systems for people?
Sure. That's a great application area. There's actually a research institute at CU that's sort of split between here and Boulder that's really focused on augmentative technology for people with disability. The cognitive ones are important. They're sort of coming, and they come in a variety of ways. So there have been cochlear implants that have worked well, that have done sort of external signal processing and then directly interface with a nerve to give people a sense of hearing. That's kind of coming down the path. There's a lot of folks working on, although it's still a research issue, it hasn't been implanted in anyone, the equivalent for retina. So it may be possible to, at the sensory interfaces, provide technology that restores some function. I don't know about you, but I call this little box I have in my pocket my exobrain, and it helps me remember to do things and is in a wide variety of ways supportive of my daily life and everybody else's, I would imagine. There are more particular ones that are being worked on for particular deficits. I'm not an expert in the area, but I'd be glad to try and follow up and give you some examples. Yeah.
Kind of like a real broad question, but who are the entities that you think are pushing this forward in the most productive direction?
Academics. I think that the commercial folks, and I'm going to pick on IBM because I took $1 million supercomputer from them. I have great relations with IBM. I know a bunch of the people who are on the basic science team that produced Watson, which is an amazing achievement. Okay, the ability to play Jeopardy at that level was really shocking and impressive. It just didn't translate into medicine. And I'm pretty close to the IBM decision-making that sort of led them to try and apply the technology into medicine. And it was all about where the money was. Okay, where can we apply this in ways that we can imagine making a third of our business out of this? And so I think that got us into trouble. That got IBM into trouble. And cognitive computing division is not performing the way IBM thought it was going to be. It'll probably be reorganized. When I pitched them about what Watson would be good for in the healthcare system, because they had already sort of decided what that was going to be, I said the real issue there is in dealing with insurance people who have to follow a huge stack of rules about what's permitted this week and what the rules are to allow this particular procedure. And those rules change all the time, and it's an enormous amount of material. It's exactly what Watson is good at. It's a short answer question, right? It's just like Jeopardy. And so they didn't think that was profitable enough. There wasn't enough money in that. They were going to go into oncology. What can you do? I kind of trust the FDA on this. I think they've been accused of dragging their feet and slowing things down, but I think that's probably an appropriate role for them. I don't agree with all the decisions they've made. They don't have the equivalent of communications requirements or technovigilance requirements yet. I think that will probably come. But I think that Gottlieb has done a pretty good job of approving things that are obviously good, but bringing the bar up fairly high. One of the problems in this is that your AI colleagues in computer science departments or computational, biomedical informatics departments don't understand the care that you deliver well enough to come up with things that are useful. So I think that the real trick here is developing collaborations where we come to understand each other better. And this is why I enjoy talking with Dustin. We both have bad intuitions about each other's work. What's hard, what's easy. And I think in particular, people often have bad intuitions about what's hard and what's easy for computer programs. And so some things that seem almost miraculous are actually, pretty easy for us to do. And some things you think, oh, it ought to be easy. If you can recognize, if Alexa can understand, what music I want to put on, why can't I just dictate my notes into a system? And Foster Goss, who's a faculty member here, who does natural language processing in clinical environments, has just one after another of these great examples of transcription systems gone horribly awry. My favorite one is he was talking about, it was a transcript of a doc who was saying that a woman was likely pregnant. She had missed her period, and the transcription system turned period not into a word, but into a punctuation mark. And she got a drug that she shouldn't have gotten because the transcribed note didn't capture the fact that she was probably pregnant. So that's an easy example, but there are going to be lots of those, and we need to understand those failure modes and those kind of errors in order to do this well. So I think that the people you should trust in this area are your colleagues, but only carefully. Yeah. My car does not have autopilot. It has cruise control, and I do use a fair amount of this stuff. So I would be very cautious about the autopilot features, and the reason for that is because there's bad interactions between the human pilot and the autopilot. So the crashes that we know of that have happened in autopiloted cars are ones where the human driver had enough warning to be able to avoid the accident, but didn't act on it. And the problem is they work so well, 98% of the time, that we stop paying attention. And therefore, the very small percentage of the time the car isn't working, we're not vigilant enough to notice it and intervene, even though we could have. And so I really worry about the interactions between these kinds of systems. And I would love an autopilot, not even that, a cruise control on my car that would know when I got too close to the car in front of me and would automatically slow down for a little while so I could wait for that guy to get out of my lane. All right? That I would trust. The one where, you can turn to your buddies and play pinochle in the back seat while it's driving for you, I'm not there. And so you got to have a sort of systems mentality about this stuff. You have to understand what the risks are. And I'm a slow adopter. I am not a rapid adopter. It depends on in what, but in things that aren't matter. And so I got fun of, I have a sticker on the back of my computer that says campaign to stop killer robots. That's not a joke. That's a real thing. There's a UN convention on conventional weapons, which was where landmines were banned. And before that, right now, is a bunch of arguments about banning autonomous weapons. So AI systems should not be able to do target selection and use lethal force. It's controversial. There's a lot of people in the U.S. military who don't want that to happen, who would like those things. And my bottom line is when the decisions are so consequential, when a human life is involved, then I don't think we're anywhere near the point where I would trust an automated system. And particularly for offensive weapons, right? So when you're looking at something coming in at you and you want to know if you're going to shoot at that, I can imagine examples where it's just too fast. But otherwise, we need accountability for the errors, right? And so computer programs have no interest in accountability. Nobody cares. They don't care if they're shut off. They don't care if they are sued for a lot of money or go to jail or any of that stuff. And as these systems get complicated, it gets really hard to point fingers about, was it the designer? Was it the purchaser of the system? Was it the vendor of the system? Was it the doc who was standing in the room? Whose fault is it that something bad happened? And so I think we're going to need to, for a lot of these things where the consequences of a bad decision aren't so devastating, then sure, rely on the AI system. And when it fails, it fails. It's pretty reliable. But for things that are really critical, then it's not just human in the loop, it's human in making the decision. Yeah?
So you made the comment that you didn't think radiology would be obsolete.
I don't think radiology would be obsolete.
But it seems some of the basic radiology tasks could be captured.
Yes, exactly. But this is not new, okay? Medicine is like this everywhere. I won't use an example from radiology because I don't know it that well, but no pathologist reads pap smears anymore. Okay, pathologists used to spend enormous amounts of time looking at cell smears. Okay, but it's really, we've had programs now for 30 years that are really good at that. And every once in a while it spits something out and says, I can't tell, and it's usually an artifact or bad prep or something like that. But pathologists still have jobs. Okay, it's just parts of it that are now automated, and it frees you up to do the more interesting things. And so there's plenty of interesting calls to make for radiologists. And like the example I showed with the, sometimes programs can see things that people can't. It might be possible for radiologists to do a better job with these tools than they could have done without them. But I really don't think that anybody is going to, we should still train radiologists. Maybe, how many we need of each specialty kind of does depend on the technology. And it's possible that we'll need fewer radiologists. One person will be able to cover a lot more service, but not yet. I'd be more inclined to believe that the cars, self-driving cars, will probably be here before automated radiologists. Yeah.
Are there other examples of kind of consumer patient level AI, like you mentioned the cell phones that could detect retinopathy that you could
Yeah, that's not fielded yet. There was just a big experiment in India to see if we could make that work that Google paid for. That stuff is coming down the pike. There's a lot of sort of consumer health stuff that's bullshit on phones, right? So this, what diet should you take, and things like that. There is some that's genuinely supportive of folks. A lot of the best stuff is not AI so much as social networking. So things like Patients Like Me that hook up people who are in similar situations, especially in relatively rare situations where you're not going to have a support group available to you locally. The social media version of this has turned out to really be helpful to a lot of patients in a lot of circumstances. The consumer-focused stuff, if we could find some app that would actually drive people to exercise a little more or eat a little better, that would be a miracle, and maybe it's possible. Certainly people buy and download those diet apps all the time. So the question is, can we make them effective? And maybe the answer is yes, right? It would be nice if we could do that. And you could imagine hooking up one of these reinforcement learning systems to your app and your scale, and maybe it would do a good job of rewarding you in ways that just looking at the scale with your own eyes wouldn't do. Especially if it paid attention, if it, you take a picture of everything you eat and then you hook it up to your scale, and it might say, hey, you know what? It was that third glass of wine you had last night that is doing that to you. Don't do that anymore. And so, it's possible that we could have consumer-facing things that were really useful in changing behavior. And, from a lot of perspectives, the biggest thing we could do for consumer applications are going to be behavioral health. We're going to get people to wear their seatbelts and not smoke and exercise a little bit and that sort of stuff. And it's really possible that these tools will be useful in that. Lord knows they drive you to buy more stuff. Right? I mean, the major application of this is getting you to click, on the more expensive thing, or to, buy from Amazon again, or click on that ad. Boy, did we put a lot of effort into that. And so I think more or less the same kind of things could nudge us to somewhat better health behaviors. Yeah.
Do you have any resources or you train your data using your normal data set, right?
Mm-hmm.
How do you have a point of reference for how to better train your data when you're adding the abnormal?
Yeah, that's sort of a complicated question. It's really more how do you develop a good training set for a task that you want to do? There's lots of places that can go wrong. There's a wonderful example where the U.S. military was trying to train systems to recognize tanks in images. And they took a bunch of pictures of tanks, and then they took a bunch of pictures of things that weren't tanks, and they took the pictures of the tanks in the morning and the things that weren't tanks later in the day, and the system was really good at picking out the stuff in the training data, but it turned out it was actually really sensitive to time of day and had nothing to do with what the image was, and so it didn't generalize very well. So there are a bunch of things we can do to be able to tell whether your system is working. It's almost the way we do clinical trials. You want to go to another site, get a source of data that isn't your source of data to test things on. with respect to generating a system that doesn't have those problems or coming up with a good data set, it's a little bit of an art. As Dustin and I were talking about and trying to develop systems that he's interested in, the hardest part of this is getting the right question. What is it that we could get these systems to do? And once you have the right question, then you can probably find data that bears on answering that question that's good. There are some sort of rough rules of thumb, so be really careful about confounders, like that time of day example. But there's no simple rule book about how to develop good data for training a system, or even a good question. So the best thing you can do is look at examples. Find ones that have done something that's successful. It's kind of in your neck of the woods. Say, oh, okay, well, that's kind of interesting, but what I'd really like is one that did this, and here I have 10,000 patients that I can put into these bins, so maybe I can come up with one that'll do whatever that is. I'm cognizant of the time. If anyone has one last question, that'd be great. Otherwise, I really appreciate your attention. I hope this was useful. All right.